Okay, so this is joint work with John Kleinberg and Sigal Loren. And so we're going to be talking about present bias, which is the tendency to value your time in the present more than your time in the future. And this leads to procrastination because you say, well, I really don't feel like doing something now, but I think I'll feel like doing it in the future. So this is part of a line of work by both computer scientists and behavioral economists that seeks to understand how people plan and carry out tasks. And so kind of a simple example is just when you, say, buy a gym membership. You buy this membership and you plan to, let's say, regularly attend the gym for the next month. But somehow when it actually gets to the time to go to the gym, all of a sudden going to the gym seems like this arduous task that you no longer want to do. So what we're looking to understand is why do people plan in this way and how can we characterize their plans? And specifically we'll be looking at sophistication. And kind of in a nutshell, sophistication is awareness of your own bias. It's understanding that you do have a bias. And so we'll be looking at when is sophistication good as an agent, when is it bad, and then how can those negative effects be mitigated. But in order to talk about sophistication, we need a framework for what a task looks like. So John and Sigal introduced this framework in 2014 where we model a task as a directed acyclic graph. And so you start at some node S, you need to end at some node T, and along the way you can take some path through this graph which corresponds to how you actually complete your task. And the edges have, to start with, the edges will have costs on them. And so the structure is, from wherever you are, you say, okay, here's the path that I plan to take. You take the first edge, you make a move, and then you repeat the process. Now you're at a new node, and again you plan, move, and repeat. And so optimally you would just take the shortest path through this graph and life would be great, but agents are not optimal. Or at least human agents are not optimal. Okay, and so just to make this more concrete, we'll look in the sample task where you have some work to do. Maybe you have to prepare a talk. And you can either do it Thursday, Friday, or Saturday. And each day has an opportunity cost associated with it. And so we'll come back to this as to understand what sophisticated agents do. But kind of as with many domains, it's first easier to understand what naivety looks like. And so naive agents, these were studied by John and Sigal in their previous paper. And if sophisticated agents are aware that they're biased, naive agents, in contrast, are unaware that they're biased. So they actually think that in the future they'll act optimally. And this is not as crazy as it sounds. And so this actually makes them time inconsistent because they'll plan to take a specific path, they'll plan to get their work done in some way, but then somehow when they actually get to the time to do that work, they decide, oh, I'm actually going to change my plan. I don't feel like doing it today. Okay? And where you might see this in your own life is maybe you decide I'll prepare for the talk tomorrow, and then tomorrow comes and something else seems more important, and you leave it for the next day. That's an example of time inconsistency. And so the way that they'll interact in this model is that from a given node, all immediately outgoing edges seem to be multiplied up by some factor of b, which is their bias parameter. So the immediate costs seem more expensive than they actually are. Okay, and so now in this kind of new graph where the immediate costs are multiplied by b and everything is the same, the naive agent takes the shortest path, and that's the path with the lowest perceived cost. Now, when I say takes the path, I mean they plan to take this path, but in fact, all they get to do is make one move, and then they have to plan again. Okay? And so what this looks like is, if you're at some node u, these outgoing edges with costs x and y are multiplied up by b, and everything else is the same. And it turns out that naive agents can be exponentially bad compared to optimal. Okay? And the simple example is the one shown here where each day the cost of doing work is exponentially increasing, but each day you also feel like procrastinating. And so kind of mathematically what this looks like is when you're at S, you could either go directly to T, but that looks like it costs you BC. If you were instead to wait for a day, and you would incur a cost of C squared, which seems smaller. So you decide it's better to wait for a day, and you do so. But then the next day, doing the work today seems like BC squared, and procrastinating for another day looks like C cubed, so you wait for another day. And so on. This goes all the way, and you're forced to increase a cost of C to the power 6, which is exponentially worse than optimal. And so the key mistake that a naive agent makes is that in their plans, they plan as if they'll act optimally without bias. Okay? And so in contrast, what a sophisticated agent does is it plans as if it'll be biased in the future. It knows that it has this bias, and knowing that it has the bias doesn't mean it's going to eliminate this bias. It is an inherently biased agent. Now, what knowing this bias does, it helps it plan for the future. Okay? Again, it's still going to pick the option with the lowest perceived cost. And remember, the perceived cost is b times the cost of the immediate edge, plus whatever cost you're going to incur after that. Now, the key difference is that this cost of the remaining path, when you're talking about a naive agent, is the optimal cost from that node. But for a sophisticated agent, it's calculated according to the true cost that it'll incur. Okay? And how does it know the true cost it'll incur? Recursion. It essentially inductively computes what its path will be. If I were to go to this node, what would I do? And it can simulate its own behavior, compute what its path and cost would be, and then plan accordingly. Okay? And so this actually makes it time consistent because by definition, the path that it plans to take is exactly the path that it will take. And now, going back to the example where you can either do your work Thursday, Friday, or Saturday. Let's say this bias parameter is 2. So a sophisticated agent has to decide whether or not to do this work on Thursday. So the choice is do it Thursday or leave it till Friday. But now the question is, what will actually happen if I leave it until Friday? And so first what it does, it says, well, let's actually see. If this were Friday, the cost of doing it Friday would look like 10. But the cost of doing it Saturday would look like 9. And so the sophisticated agent knows, if I were to leave this work to Friday, my Friday self would leave this work till Saturday. And so now the choice isn't between doing work on Thursday or Friday. The choice is between either doing the work on Thursday or doing it on Saturday. And because the agent knows this, it's able to say, well, I'd rather work on Thursday than procrastinate all the way till Saturday. Okay? So this is the key difference. Whereas a naive agent would have said, well, I'll push it off until Friday, and then upon reaching Friday would have said, oh, actually, I'll push it off until Saturday. The sophisticated agent knows in advance, if I were to leave it till Friday, I would actually push it till Saturday. And thus, doing it Friday is no longer even an option. Okay? So in this case, the sophisticated agent has actually acted optimally. And you might be thinking, well, maybe they always act optimally. And unfortunately, that's not the case. So they can be off by a factor of at least b from optimal. And this is simply because, in this example, they can either incur a cost of 1 today or a cost of b tomorrow. And so they still do like to procrastinate. It's still worth for them deferring the cost until tomorrow. Okay? But it turns out this is as bad as it gets. This is the worst case. Okay? In every instance, the cost incurred by the sophisticated agent is at most b times optimal. Okay? And this is exponentially better than a naive agent. Okay? And so this suggests something kind of interesting, and this is kind of, to me, the most insightful part of this work, was the problem with procrastination and with present bias isn't actually the fact that you're biased. The problem is that if you plan as if you won't be biased, then things get really bad. But actually, if you plan knowing that you are biased, then you're doing pretty well. Okay? And this is actually not so tough to prove. So just a little bit of notation. CS will be the cost for the sophisticated agent, and CO will be the cost for the optimal agent. And we'll just make this inductive claim that from every node, the cost that a sophisticated agent would incur is at most b times optimal. Okay? And so let's say in this example that the sophisticated agent is at U. The optimal thing to do is to go to V, and the sophisticated agent chooses to go to W. Okay? The perceived cost of going to V for the sophisticated agent is just b times x plus whatever cost it would incur from V. And by induction on V, this is at most b times optimal. Okay? Now, because the agent chooses to go to W, the perceived cost of going to W must be even smaller than that. And the true cost of going through W must be even smaller than the perceived cost. Because remember, the perceived cost has this initial edge multiplied up by a factor of b, and everything else is the same. So the true cost is just that without the factor of b. And so it must be even smaller. And this actually yields the result. Okay? And now you might ask, well, what if the agent doesn't actually know its bias exactly? What if it has some believed bias, but which may not be the same as its true bias? And so actually, this is a generalization of both naivety and sophistication. Because if you believe your bias is 1, that means you believe you're optimal and you're a naive agent. If you believe your bias is B, then you're completely sophisticated. It turns out, actually, that there's this kind of sharp transition when you believe your bias to be the true bias. If you underestimate your bias, you're exponentially bad. If you overestimate your bias, you're actually bounded by your overestimate, but still a constant factor. So if I believe my bias is 3, but it's actually 2, that's still okay. My performance is now off by a factor of 3. Okay. And so now, this is all great. Sophisticated agents seem to be doing well. And the question is, now when are they doing poorly? And so it's been noticed that sophisticated agents actually do badly when trying to maximize rewards. Because so far we've been looking at a cost minimization standpoint. And in this context of maximizing rewards, sophisticated agents will actually do poorly. And the intuition is, you know that you're greedy. So it's present bias in the context of reward maximization is collecting rewards too early, being greedy. And so you know that in the future you'll be greedy. And this actually induces you to be greedy in the present as well. And so the example I'll give is, you may have heard of the Stanford marshmallow experiment, where children are given a marshmallow and saying, if you wait 10 minutes without eating this, I'll give you a second marshmallow. Okay? And so consider extending this example so you get exponentially many marshmallows the longer you wait. Okay? And now let's say you have a sophisticated child, and because it's a child, their bias will be 3. So here's the intuition. If this child is at V4, they have a choice now between saying, I could take 16 marshmallows now or 32 marshmallows in the future. But because they're biased, this child says, I'd rather have 16 marshmallows now than 32 marshmallows in the future. Okay? And so now, if the child decides, I'm going to go and collect these 16 marshmallows now consider the previous version, the 10 minutes ago self of this child. It knows I'm not going to get 32 marshmallows. It knows that if I wait 10 minutes, my future self is just going to be greedy and collect 16. But I'd rather have 8 now than 16 later. Okay? This is just a scaled down version of the exact same decision. And so it decides I'd rather have 8 now. And this goes all the way back where the child at the very beginning says, I know if I wait 10 minutes, I'll just eat those 2 marshmallows right there. But I'd rather have 1 now than 2 later. Okay? And so whereas the optimal agent would be able to actually get all 32, this sophisticated agent's only going to get 1. And they're going to be exponentially worse than the best case. Okay? As an interesting side note, if you have a naive agent in this scenario, they're actually only off by a factor of B. And the reason is, right until the last minute, they actually believe that they're going to get all 32. And then they reach this point and they decide, actually, I'll take the 16 now. Okay? And so here we seem to have a problem because sophisticated agents are doing pretty poorly. And so now the question we'll ask is, as somebody who's designing this task, let's say, what can you do to help your sophisticated agents out? How can you mitigate their bias? And so we'll look at something called commitment devices. And a commitment device is an action that you take now to mitigate the bias of a future self. And so some famous examples are Odysseus being tied to a mast. He knows that he'll fall victim to the siren's calls, so instead he has himself tied to the mast, so he no longer has the option of being a victim. More recently, there's a Chrome extension that'll block your Facebook newsfeed. And you install this now because you know, if I had a Facebook newsfeed, in the future, it'll cause me to waste time. So instead, I'll just block the entire thing from the beginning. Okay? Essentially, you're preventing your future self from making selfish choices. Okay? And this is known as choice reduction, taking away possible actions. And the way that we'll represent this in the model is just deleting edges from the graph. So let's say, as the designer of this task, you can see what your sophisticated agents would do, and you can say, if I were to delete certain edges, maybe they would do better. Okay? So going back to the marshmallow example, what if we were to remove this edge right here? Remove the option of collecting those 16 marshmallows. Now, this agent is again going to plan by this backwards induction. So it says, if I were at V3, the choice would be between 8 now or 32 later. And actually, because the bias was 3, 8 now has a value of 24, 32 later has a value of 32. And so this agent says, I'd rather have the 32 later. And so instead of collecting directly at V3, it would say, I'm actually going to make it all the way to V5. Now at V2, the option is I could have 4 marshmallows now, or I could wait. And I know if I wait, I'll make it all the way to get 32. And given the choice between 4 now and 32 later, I'll take the 32 later. And this actually propagates all the way back to the point where at the start you say, well, I could have 1 now or 32 later. I'd rather just have the 32 later. Okay, and so by removing this one edge, we've actually gotten this agent to act optimally. Now the question is this always the case? Are examples always this brittle, where just one change goes from exponentially bad to optimal? And so this is a little too good to be true. So we can see that if we were allowed to remove arbitrarily many edges, you can always get the agent to be optimal, right? Just throw away all of the graph except for the optimal path, right? So there's some trade-off between performance and how many edges you get to remove, right? And that's the trade-off that we'll be exploring. And actually, it turns out that the result is if you remove 2e over k edges, you are bounded by a factor of n to the power k in how bad you are. And in other words, you've removed an arbitrarily small constant fraction of edges, and you've gone from exponentially bad to polynomially bad. Okay, and so this is very powerful. No matter what the example is, you can always get rid of this exponential growth. Okay, and now it's actually an open question if this can be improved. We believe that it could be as good as a constant fraction as opposed to polynomially bad. Okay? And so to summarize, sophisticated agents, good with costs, bad with rewards. But as a task designer, you can take this into account to improve the performance. Okay? And so there's a few potential directions from here. One actually kind of interesting open question is, if an agent isn't actually compelled to force a task, or compelled to complete a task, how much do you have to pay them to do it? This is a tractable question for naive agents, but actually for sophisticated agents, this may be NP-hard. And then there's also some notion of this entire model assumes that you exactly know the costs and rewards on the edges, and maybe this isn't realistic in practice. Okay? And finally, you could consider mixtures of biased agents playing games with each other, interacting, and ask what happens. All right? And that's it. Thank you.
Sticking time, and we have time for questions. So, okay, I have one. You said that a nice scenario to be analyzed is with uncertainty of cost rewards. What about bias? So bias is a constant for you. What if you put a distribution rather than a fixed bias?
Yes, I believe people are actually working on this now. So the answer from here is, if you have a distribution over bias, the optimal thing to do is choose the kind of top end of that distribution, because underestimating is exponentially worse than overestimating.
Yeah, makes sense. Questions?
Showed before.
Mm-hmm.
So it holds for general graph.
Yes.
And if you have some properties, if you know some properties of the graph, like expansion or things like this, the result change?
It's possible. We have not looked into that. Mm-hmm. But I would assume so. So the basic idea is that if you're doing really badly, then there must be kind of some progression of nodes that are getting worse and worse and worse. And so a graph that looks really bad, and the ones that force you to be kind of, that make it really difficult to go from exponential to polynomial, they all kind of follow a similar structure. So I would assume that any graph that really doesn't have that structure is going to be significantly easier to deal with. This is kind of the pathological worst case.
Okay. Oh, okay.
So do you know if you can get away with less than removing those many edges?
So we've not encountered a case where you actually have to remove that many. So you may be able to take this n to the negative k and turn it into a b to the negative k, which is, instead of kind of polynomially bad, you're off by power of your constant bias.
Okay. So, go ahead.
So at least in the benefit version, it seems like the bad case happens. The bad case can be mitigated when the ratio between the best benefit and the second best is larger than the bias.
Mm-hmm.
And so if you can remove edges to attain that setting, then everything else will telescope back.
Yeah,
So-
exactly. And so the kind of pathological case is, well, what if instead of that second best, that's 16 marshmallows, what if there were just, you had to wait 10 minutes and you get 16, and you wait another 10 minutes and you get 17, and you wait another 10 minutes and you get 18. And so you can kind of add edges to make it robust towards that fix.
And so adding those edges actually means that it's harder and harder the finer you can slice the future benefits.
Yes.
Right. And then if you increase your estimated bias, then you can diminish the required gap to have poor performance.
Your estimated bias. So in this example, it was assumed that the agent was sophisticated, so there is no, the perceived bias, or the believed bias is the same as the true bias?
Yes.
You're saying if the agent were...
If the agent is sophisticated but with a poor estimate of the bias, if that happens to be an overestimate, then there'd be cases where you could do better.
So it might actually be the other way. If you underestimate your bias, then you would do better. Because in the same way that a naive agent will make it all the way to the end, if you believe that you are optimal, then you kind of will be strung along thinking that you'll get to the very end. So I think that underestimating your bias, having a smaller believed than true bias, will actually make you deal with these situations better.
Another question, if you want. Okay, if not, we can.